Hello everyone, this is part 3 of module 3 and chapter 3, the relational model and normalization. Where we left off was we broke down functional dependency, and we talked about how we have some attributes that can determine other attributes. Those attributes are called determinants, and the other attributes that are dependent on those determinants are called dependents. From those functional dependencies, we started getting into the conversation of keys and how we use keys or to determine what our keys are for our tables or our relations, where our determinants become our keys. And then we broke down the different types of keys that you need to make sure that you understand, which is what a candidate key is. And a candidate key, again, is something that is a determinant or an attribute that can determine every other attribute in that particular table or relation. Okay, that's considered a candidate key. A primary key is a key or a candidate key that we've chosen to be our unique identifier for that particular table. So once we've chosen whichever candidate key we want to use, especially if there's more than one in that table, that becomes our primary key, which is our unique identifier. And then the last term that we left off at, we talked about, was called a surrogate key. And remember, a surrogate key is supplied by the database management system, which is simply an artificial column or just a number that meets that unique characteristic, that number that never changes, numeric data type that never changes, to uniquely identify each row. So surrogate keys are provided by the database management system. So all that leads us to the term foreign key. So what a foreign key is a foreign key, by definition in the book, is the primary key of one relation that's placed in another relation to form a link between those two relations. All right. So the foreign keys is how we create our relationships. So as we've been talking about, that those common fields in each table, that we can form a relationship or link those tables together for when we query information to pull the information from two different tables or multiple tables together. We need to have foreign key values. Okay, so a foreign key can, just like a primary key, can be a single column or a composite key or two or more attributes. And then the term foreign refers to the fact that the key values are foreign to the relation in which they appear as foreign key values. So the way to think about it is, just as we think about a surrogate key as a column or information that really doesn't add any value to that particular table, you can almost look at a foreign key the same way, because really a foreign key is just is a primary key of another relation or table that may not add any additional characteristics or value to the table that is placed in, other than creating a link back to its parent table or the other table. So here's an example. Again, we have something here written in standard notation. We have the department and employee table. The primary keys are underlined and the foreign keys are always italicized. So I may have mentioned this before. If I ask you to write it in just standard notation, this is how we would write our tables out. So of course, department and employee, all caps, and in each parentheses would be your attributes, and you would indicate your primary key by underlining, and any foreign key you would italicize it so to indicate it as a foreign key. So notice here that the department name, which is the primary key of department, has been placed in the employee table as a foreign key. So it really, in this case, it does add some value to this particular table of employee by giving the department name in which that employee is associated with. Okay. Keep in mind, though, obviously department name is not a surrogate key because it does not meet that ideal characteristic of a primary key, which is short, and numeric, and never changes. Okay, obviously department name would be some type of character field that may change, so just keep that in mind. So one of the things that we need to understand is that when we use foreign keys, there's some built-in mechanisms in database management systems to help us maintain not only the relationships between those tables, but also the integrity of our data as we add, as we insert, delete, or modify information. And how we control those anomalies, or things, what the book terms anomalies, but how we control those potential errors is with the referential integrity constraint. So by definition in the book, a referential integrity constraint is a statement that limits the values of the foreign key to those already existing as primary key values in that corresponding table or relation. Okay, so that last statement down there is what we would write that would in our SQL, that would make the database management system understand what we're working with. So what you see is that SKU in the order item table must exist as SKU in the SKU data table. Okay, so if you really want to look at a complete example, notice here is a complete example. So while we have defined a referential integrity constraint to acquire a corresponding primary key value in the linked table, the technical definition of the referential integrity constraint allows for one or other options that the foreign key cell in the table is empty and does not have a value. So if a cell in a table does not have a value, it is said to have a null value, and that's what we'll talk about in chapter 4, null and not null values. But in this case, it's difficult to imagine a foreign key value having any null values in a real database with the referential integrity constraint is when it's in use, because obviously primary key values are going to be our indicators, unique indicators of each row in our table. So of course those values cannot be null. So anytime that you think of primary key values, they typically cannot be null values. So in this particular example here with SKU data and order item, and in our referential integrity constraint statement down there where we said order item dot SKU, so that means SKU and order item must exist as SKU in SKU data. Those values must be the same. So we can't. So essentially, what we're saying is we cannot add another row in order item if the value in the SKU column does not match a existing value in the SKU data column. Excuse me, in the SKU data table. Okay, so whatever we're adding in order item, and we're adding that row line, when it comes to that SKU column or that SKU value in that row, it must match a SKU value that's already in the SKU data table. Essentially, that's what it's saying, and then the database management system will control that and make sure that we don't violate that rule. Okay, so referential integrity constraints ensure that updates, deletes, and insertions are controlled, making sure we maintain the integrity of our data. This way, any unauthorized users do not result in any kind of data loss, or it also guards against accidental damage to the database as well. But these mechanisms, because these database management systems are built on the relational model, as we discussed, these mechanisms are typically built in, especially with what we're working with Microsoft SQL Server. So if you add that integrity constraint, it'll do most of the work for you. Okay. So up until this particular point, we have discussed 3 different types of constraints so far in our discussion. Remember the domain integrity constraint. Remember that had to do with the same type of values in a column that limits the type of values. The entity integrity constraint, which we just discussed before with the keys, and now our referential integrity constraint in regards to the values of our foreign keys that must match the primary keys. So the purpose of these three constraints is to create database integrity, which means that the data in our database will be useful and meaningful at all times. Okay, and again, this is really referencing and targeting an operational database that's that has a number of different daily operations that where data is changing all the time, or new data is being put into the database at all time. We need just to make sure that we have some rules in place to control the structure of what we're putting in, and then control any errors or possible problems as we change, delete, or modify any information. Okay, so when we do modify things, we need to understand what modification anomalies are. That's what the book talks about in regards to the potential errors of our operational database that can happen. So in this particular example here, in the equipment repair table, in terms of an incorrect update operation on acquisition costs for the equipment type of drill press. So here's an example here. So notice our drill press item number, which is 100, and the acquisition cost is 3,500. What it's saying here is that if we change that, what kind of potential anomalies can happen? Okay, what kind of potential anomalies can happen? Notice in the bottom, the top table, we have item number 100, which is, if you look down, there's 4 entries for item number 100, and then if you look at the acquisition costs, they are obviously is 3,500. Okay, if we needed to change that acquisition cost from 3,500 to 5,500, notice in the bottom table there where only one line has been changed. So only one line, which is line 6, or that row, has been updated. How can we make sure that all rows that are associated with that particular item number can be updated at the same time? So that's kind of what some of this referential integrity and stuff that we can put in can help us take care of, because this is considered an insertion anomaly, which of course messes up the integrity of our data. So the book talks about 3 different types of modification anomalies: deletion anomaly, insertion anomaly, and update anomaly. What we just looked at, of course, was an update anomaly with the example of acquisition costs with the same item of equipment that appears several times. However, we need to make sure that we update each row that's associated with that. So this is these inconsistencies what we talk about are considered those type of data integrity problems that you can come along, that can happen. Okay, so understand that as we talk about it, the database management system that provides these resources for our referential integrity constraints can kind of handle a lot of that for us. Okay, so now at the end, we're going to get into talking about normal forms, but please understand that with normal forms, you must start, in order for us to really get into normal forms, you must understand functional dependency. And then once we get from functional dependency, and then we understand how to determine and identify what our keys are going to be, and then what our non-key attributes are going to be, now we can really discuss what our normal forms are, or how we're going to categorize our information. Okay, so for this particular class, as we discussed, we're going to concentrate on making sure that all of our tables are put into Boyce-Codd normal form, or BCNF. So if you see there, the source of the anomaly that we're talking about is functional dependency. That's where we're going to spend the most of our time. Okay. Now this particular chapter does talk on multi-value dependencies in 4th normal form, where we move each multi-value dependency to its own table. So we will talk about that. However, we will not get into data constraints and oddities, which is the 5th normal form in DK and F. Okay, we won't discuss that in this particular class. Okay, so as we talked about is, to key or not to key, that's the question. Okay, If we back up a little bit, we want to start with first normal form. We define first normal form as a table that meets the conditions or characteristics of a relation. Remember, we already discussed that. And we have defined a primary key. So if it meets the characteristics of a relation that we talked about, those number of different characteristics, and is defined as a primary key, then it's in first normal form. Okay. So if we really want to break down everything, kind of taking a look at it, a table that qualifies as a relation is in the first normal form. Second normal form, what you're looking for is a relation that's in second normal form is if all of the non-key attributes are dependent on all of the primary key. Okay, so if you want to simply put this simply or break it down, second normal form would only apply to if you have a composite key, composite primary key. So if you have a composite primary key, what it's saying here is that all of the non-key attributes in that table must be fully functionally dependent on all of the composite key. So both of the attributes. Remember our little matrix or formula that we had where if A and B determines C, then neither A nor B by itself can determine C, right? That's why that's what we talk about full functional dependency for second normal form. So if you need to go back and review that, make sure that you understand full functional dependency. And then third normal form is a relation that's in third normal form if it's, of course, in first normal form already, and it also meets the rules of second normal form, and then it has no determinants except the primary key. Okay, and I'm going to throw out a new word for the third normal form that you may see in the book, and you may see is that you can't have any transitive dependencies. Transitive dependencies would be a non-key attribute that can determine another non-key attribute. Okay, you can't have that. If you have a non-key attribute, something other than the primary key, that can determine another attribute that's not a primary key, then that's considered a transitive dependency. Okay, so you have to eliminate those for it to be in third normal form. Okay, and then lastly, is the Boyce-Codd normal form, is whereas a relation is in Boyce-Codd normal form, and if every determinant in the table is a candidate key. So if you have make sure that your primary key is a candidate key, then that particular table is in Boyce-Codd normal form. So that means that your primary key can determine every other column that's in that particular table. Okay, 95% of the time, I'll put 95% on it. 95% of the time, if your tables are in third normal form, then they're most likely going to be in Boyce-Codd normal form, and you're in the head of the game. But there are some cases where you may have to take a look at it again, especially if you have multiple candidate keys in that particular table. Okay, so the last bullet point there is just a saying that the book used. I swear to construct my table said that all non-key columns are dependent on the key, the whole key, and nothing but the key, so help me Codd. So that's Codd's little interesting little phrase that he used. So first normal form would be on the key, second normal form would be the whole key, and then third normal form would be nothing but the key. So that way, again, third normal form, Boyce-Codd normal form would be almost the same. Okay. So here is the process that you need to understand for putting a relation into Boyce-Codd normal form. Okay. And the book kind of breaks this down, and we'll do an example here of how we can do this, but this is very, very important. If you understand this, then you'll do well on tests, quizzes, the homework, and everything else. So the first step in putting a relation or a table into Boyce-Codd normal form is to identify every functional dependency. Okay? So remember, we start off with functional dependency. So when we go through our functional dependency process, we identify what our functional dependencies are, what our determinants are, and what our dependents are. Once we determine that for every one of our tables, we need to identify every candidate key. Remember, a candidate key would be a determinant that can determine every other attribute that would be in that table. So that's considered a candidate key. Okay. So now number three is the key point, because this is where you're going to be. We begin our decomposition process of where we may need to break down our tables and create more tables. So if there is a functional dependency that has a determinant that is not a candidate key, so we have a determinant that does not determine every other column in that table, then we move through the steps of A through D. Okay, so what we'll do is we'll move the columns of that functional dependency into its own table. We'll make the determinant of that functional dependency the primary key of the new table or relation, and then leave a copy of the determinant as a foreign key in the original relation or table. Okay, and then create a referential integrity constraint between those two tables to enforce that particular relationship. Okay, and then the fourth step would be to repeat step 3 until every determinant of every table is a candidate key. And then once we've done that, all of our tables are broken down into Boyce-Codd normal form, and then we can move on. Okay, in the design process. So here's an example of a table that we want to put into Boyce-Codd normal form. So we have a table of 6 different columns of item number, equipment type, acquisition cost, repair number, and repair date, and repair costs. If we wanted to break these down into what our functional dependencies are, our functional dependencies would be this. So at the top there in standard notation would be our table. We've determined that item number determines type and acquisition costs, and then repair number determines every other attribute in that particular table. So repair number would be considered a candidate key, right? So if that's considered a candidate key, that particular determinant, and then item number is a candidate key that is a determinant that is not a candidate key. So remember, we need to make sure that we put that in its own table. So notice now equipment repair becomes 2 tables, and now item, where item number was the determinant of the determinant that wasn't a candidate key, now becomes a primary key of the new table, with type and acquisition costs as its non-key attributes, and then we leave a copy of it as a foreign key. Notice in repair number, in repair table, italicized as the foreign key to enforce that relationship. And then in our fourth step, where we add a referential integrity statement that can enforce the relationship between those 2 tables, the new table of item and the repair table, with item number being our foreign key value. Okay, so notice how we kind of broke everything down, starting with functional dependency, and then moved through our Boyce-Codd normal form process. So our new 2 tables would look something like this. Okay, so now in our tables are both in Boyce-Codd normal form, and we could move forward. Okay, one more example here would be if we wanted to start off with, say, just go from first normal form, second normal form, and third normal form. Here, if we just wanted to check against this table here with SKU description, department, and buyer, is this in first normal form? It's in first normal form because it meets the qualifications of a relation. So if it meets the qualifications of a relation, we're in first normal form. Okay, so when we start breaking down our functional dependency and looking at step 2, notice here in standard notation, again, there's our table up at the top there, and our functional dependency, we see that SKU can determine every other column in this table, and also SKU description can determine every other column in this table. And then buyer determines department. So both SKU and SKU descriptions are candidate keys. And then buyer is a determinant that's not a candidate key. So we know that we have to go through our step 3 process with buyer and department at this particular point. But in terms of second normal form, because we don't have any composite keys in this table, it automatically is in second normal form. Remember, if we don't see any composite keys, we can move on to third normal form. So because all non-key attributes are determined by SKU and orders determined by SKU description. But in this case, it looks like we would choose SKU over SKU description because SKU would be more closely related to our ideal characteristics of a primary key. So if we wanted to take a look at this for a third normal form, again, we're looking for, again, those transitive dependencies. So in this particular case here, we've already determined that SKU and SKU description are candidate keys. We've already determined that it's in second normal form because there's no composite keys. However, in this particular table here, because buyer determines department, that's considered a transitive dependency. So that means that it would not be in third normal form unless we remove buyer and department and put it in its own table. So that's what we're saying here, is that that would be considered that transitive dependency or a non-key attribute to determining another non-key attribute between department and buyer. So therefore we break out buyer and department into its own table. Notice here now we have two different tables. We have SKU data _2 table that we've created. We've moved buyer and department into its own table while leaving the buyer as a foreign key that maps back to the new table, and then adding our referential integrity constraint statement to enforce this relationship. So if we look at those two tables, now both SKU _data 2 is in third normal form, and our buyer table is also in third normal form. Okay, and then the last step is Boyce-Codd normal form, where we'll take a look at it and make sure that all of our determinants are candidate keys for both. Okay, so in this particular case, both of them are candidate keys for each one of the tables. Okay, there is no other determinants in either table that aren't candidate keys. And here, this is what the two new tables would look like. Okay, so ideally what you would want to do is you would want to be able to take this particular table and kind of go straight to Boyce-Codd normal form. Okay, and you don't necessarily want to go, okay, is it in first normal form or is it in second normal form, and then let's go to third normal form and then fourth normal. You know what I mean? Boyce-Codd normal form. You don't want to necessarily do that. You want to be able to look at a table and determine what those functional dependencies are, and then from those functional dependencies be able to go straight to Boyce-Codd normal form. And then that's what we see here. That's exactly what we did, is that if we understand the step-by-step process of putting a table in Boyce-Codd normal form and how we break down and decompose these tables, it becomes fairly simple. So we've already determined here what our functional dependencies are, with SKU and SKU description being candidate keys, and then buyer is that one transitive dependency that we know that we are going to have to put in its own table. So we should be able to go straight from our our table here, where we know that we need to break this down because of this particular functional dependency between these two attributes, understanding that we now need to split those out into its own table, and then adding that referential integrity constraint. So we just have to be able to identify functional dependency and then go right to decomposition process of figuring out how we need to decompose and put our appropriate determinants and dependents in their associated tables. And again, here's where we what our tables would look like after the decomposition process. Okay. One of the last things that Chapter 3 talks about is multi-value dependency. Multi-value dependency is one of the tougher things to understand from a functional dependency type aspect. But by definition in the book, a multi-value dependency occurs when a determinant is matched with a particular set of values. So look at the examples that we have here. So an employee can have Notice if I ask you to show multi-value dependencies, make sure that you use 2 arrows instead of 1 arrow for the functional dependency. So the 2 arrows together indicate a multi-value dependency. So an employee can have multiple degrees, right? A employee can have multiple siblings, just like a part kit will have multiple parts. So the key thing is that when we put these into their own, the rule is that if you have a multi-value dependency that meet these type of characteristics, you just need to split those out into their own tables. But we need to understand that one of the rules is that a determinant of a multi-value dependency, so in this particular case, we have 3 different determinants of employee and part kit. They can never be a primary key. So these tables, so this is what our tables would look like in regards to our multi-value dependencies. So in our multi-value dependencies, notice we have our employee name, and notice that it can be associated with multiple degrees. So in that particular table, even though employee is a multi-value dependency with degree, but notice our employee name cannot be considered a primary key. So these tables would not have a primary key value. Okay, they wouldn't have a primary key value. So just understand that in terms of what the rules are. So if you understand that, you'll get by on what we need to do in regards to tests and your quizzes and assignments. This is what we talked about in regards to fourth normal form. So eliminating these anomalies that are associated with multi-value dependencies. The rules are you just put them into a separate relation or their own tables, and then this is known as fourth normal form. So when we see fourth normal form, we understand that this is just a process of breaking down those multi-value dependencies. Okay, and this is the end of part 3.